the Physics Odyssey channel. I am Vinni Physics, where I'll get up here and talk about physics, even if there is only one person in the world, or dog, listening. This happens to be our new little dog. She's a little Westie, little puppy. Cutest little thing. Up and coming content, more busting Mythbusters, some virtual myth busting, and I invite you to submit a scenario. If there's something cool in the world you see and you want to know how it works, submit it. And if it's not too difficult, I'll give it a shot. Physics of stupid stunts, plenty of those out there. We're going to do one of those today. Astrodynamics using simulators, amusement park physics using simulators, do some Blender animation to demonstrate some really cool advanced physics. And then eventually we'll get to quantum mechanics and relativity for all. Try to make that fun. I've got some really cool visual quantum mechanics, and I think that's going to be some fun. So if you want to see the future content or you like this content, subscribe and I'll send you a notification when I post new videos. Okay, today's topic is Science of Stupid episode. The topics we'll get into related to physics, torque and counter torque, and conservation of angular momentum, Newton's second law in angular form, the center of mass, moment of inertia, of course, not smart human decisions. But let's first go ahead and take a look at the episode, and then we'll come back and talk about the physics.
Now watch what happens when a simple round of golf goes very, very wrong. Yeah, other than being stuck under a golf cart, yeah, you're totally good, dude. Look, I'm not a huge golfer like that guy, but I can tell you why it's best to drive golf carts on even grounds and at normal speeds. Axle width, compared with the low profile, gives an empty golf cart a low center of gravity. That makes it as stable as a car. As soon as people are at it, the center of gravity rises by up to 50%, which makes it much less stable. So when turning or on a slope, it doesn't take much force to tip it. Once the center of gravity moves outside the wheelbase, over it goes. This charitable couple has been good enough to offer a lift to these, well-fed gentlemen.
Okay, notice initially they're on the back of this cart, so they've shifted the center of mass up a little bit and in this direction. But the cart is not rotating about this point.
They're going to learn something about the shifting the center of gravity the hard way. Ow! That's not good. That shifted. Definitely shifted. Golfers take note. The center of gravity can shift backwards as well as sideways. That's why you should always be careful when driving your golf cart. In the business of tree chopping.
Okay, so I'm going to get into a lot of detail about why, when the gentleman initially stepped on the back of the cart, it didn't tip over, but when they backed up and came to a stop, it did. But let's first talk about what is torque. So we know that force is needed to provide for the acceleration of an object. Torque is what is needed to provide for angular acceleration. So force, accelerate in that direction. Torque, accelerate in this direction. The equations for it are the magnitude of torque is the force times r, which is the distance from the force to the rotation axis, times the sine of the angle between these two vectors, and that's equal to the moment of inertia times the angular acceleration. In vector form, it's r cross f. Okay, here's an example I use a lot for students I think is helpful. And that is a wrench. So you've got a wrench here, and it's being used to tighten this bolt. The force is being applied at the end of the handle, a distance of r from the rotation point. So what is the torque? The torque is equal to that distance from the rotation point to where the force is being applied, times the force, magnitude of the force, times the sine of the angle between this r vector and the force vector, that. This is actually an important quantity. It's called the moment arm or lever arm, and that's simply equal to the r times the sine of this angle. And that happens to be the component of this r vector perpendicular to the extended line of force. So a lot of times in a problem, you won't have this angle, but you'll be able to see this r perpendicular, again, perpendicular to the extended line of force. Okay, so now I'm going to apply it to a seesaw, where here we have torque due to two different forces. And the force is gravity. So this equation, the general equation for torque, becomes this, where the force is the force due to gravity, which is simply the mass times acceleration due to gravity. R is the distance from the mass to the point of rotation. The sine of the angle. Again, the angle is the angle between this force vector and this r vector. Okay, we have two things torquing about this rotation point. One of them is this mass of 2 kilograms, and the other is this mass of 1 kilogram. So let's plug in the numbers and find out the total torque about this point of rotation. Okay, so mass times g, which is 9.8, times the r, 1 meter from the rotation point, times the sine of 80. This is this angle. Okay, I've got a plus here, because that's going to provide for a counterclockwise rotation. We're in the xy plane here, so that's defined as positive. Counterclockwise is defined as positive. The 1 kilogram mass times 9.8, it's also a distance of 1 meter from the rotation point, times the sine of 100. Okay? Clockwise rotation, so minus. Plug that into your calculator and you get 9.65. And the units for torque are newtons times a meter. Okay, so we've got the torque, but we really want to know the acceleration, the rate at which this thing is rotating about this point. Okay, so the equation is torque. This is torque. Is equal to the moment of inertia times the angular acceleration. So what's the moment of inertia? The moment of inertia describes how the masses are distributed about this rotation point. For a point mass, it's mass times the distance to the rotation point squared. For a thin rod, which is what I'm assuming here, it's 1/12 times the mass times the length of that rod squared. So plug in the masses. 2 kilograms for this, 1 meter squared, plus 1 kilogram times 1 meter squared, plus 1/12 times the mass of this thin rod, I'm assuming it's really light, 0.1 kilograms, times its length squared. So here's the moment of inertia about this rotation point. 3.033. So here we have a torque. This is the torque. This is our moment of inertia. And this is our unknown. Okay, divide both sides by the moment of inertia, and I got an angular acceleration of 3.1 radians per second squared, actually. Okay, I don't know about you, but I don't walk around thinking in terms of radians and radians per second squared. I'm more familiar with degrees. 360 degrees is the number of degrees around a circle. So convert radians per second squared to degrees per second squared, and that gives us 177 degrees per second squared. So I forgot my second squared there. The rate of acceleration is not constant because as this thing rotates, the angle rotates. So the torque due to gravity is changing as the thing is rotating. It's not constant. But at this instant in time, when the angle between this extended r and the force vector is 80 degrees, this would be the angular acceleration. Okay, there's something really important. It's called the center of mass. So what is the center of mass? And I'm going to compute it for this problem. Okay, the center of mass, say along, let's call this the x-axis. Center of mass is equal to the mass, one object, times its distance from the origin. And I'm creating a coordinate system where the origin is right here at the rotation point. So this is x equals 0. So x1 plus the mass of the other object times x2 divided by the sum of the masses. Okay, so I'm going to plug this information into this equation and I get a center of mass of minus 0.33. So gravity will act as if all the mass is located at that point. And if the center of mass is not at the origin, this thing will rotate. If it's to the left of the origin, the object will rotate this way, counterclockwise. And if it's to the right of the origin, it'll rotate clockwise. So what I found interesting about this video was that when the men initially boarded the golf cart, it didn't tip, and that's fine. That's not hard to understand that. But then when they started to move backwards and braked it, they did rotate about this point. So before I continue, why didn't it tip when they first stepped on? So if you want to pause the video and discuss this with your students, feel free to do that, and I'll be back in a minute. The physics before applying the brakes, kind of like a seesaw, which is what we looked at a few slides ago. So the rotation point in this video is this back wheel. So before they stepped on the back, the center of mass was probably somewhere around here. Okay, when they stepped on the back, it moved the center of gravity up and also towards the back. And I want to say right above the back wheel. Somewhat arbitrary, but that's probably pretty close to where the center of mass was shifted. If the center of mass would have shifted to the left of the rotation point, gravity would have taken over and torqued it counterclockwise. But obviously, that didn't happen when they first stepped on it. So the center of mass must be above this rotation point or somewhere in this direction. So how do you find the direction of torques? Okay, gravity is a force, and it will cause a torque about the possible rotation points. So the golf cart could rotate about this point, or it could rotate about this point. So let's take a look at those. How do you find the direction of the torques? There are your hints. Okay, use something called the right-hand rule. And let me explain what the right-hand rule is. First, let's analyze the torque about this rotation point. This is the equation for the magnitude of torque. It's the force times r, which is the distance from the rotation point to where the force is being applied, times sine of the angle between them. And as I mentioned before, this is r perpendicular. So torque about the back wheel due to gravity. The distance from the rotation point to where the force is being applied is R2. The force is gravity in that direction straight down. The r sine theta is this. Here's my r perpendicular right there. So if I have that length, I can plug in mg times this length, r perpendicular. And I can get the torque due to gravity. But here I'm not concerned about the magnitude of the gravitational torque. I'm interested in the direction. So the way to determine the direction of the rotation is you put both vectors, r2, and the gravity vector is straight down at the origin of a coordinate system, and you apply something called the right-hand rule. And that just means to grab the first vector in this equation first, and then the second vector second. This is my F equal mg. And my fingers, see how they're curling, they're rotating? That's the direction of the rotation. So gravity will cause a torque in this direction about this point. Applying the same logic to this possible rotation point, here's my r vector, gravity down. Grab r1 first and then the force second, so it's going to rotate this way. So there you have it. Now my r perpendicular here is much greater, so this gravity will exert a greater torque about this rotation point than it will over this rotation point, and it's towards the center, not outside of the, not this way about this point. And this is why you did not see the thing rotate when the gentleman boarded it, because the center of mass was here or somewhere to the right of there. And that can't cause a rotation about this direction, which is what we saw. About this rotation point. But clearly, this rotation, this torque is greater than this torque because this r perpendicular is greater. So why isn't this thing turning about this wheel right here? I think the obvious answer is because you've got a surface here. So the surface here is providing a counter torque. And we can actually compute those counter torques. And this is what it looks like. So there is a torque due to the contact with the ground about this point. Okay, this R3 vector is pointing from this possible rotation point to where the force is being applied. And again, the force is the normal force straight up. With this vector at the origin, normal force at the origin, I'm going to grab the R3 vector first, and then that vector, right, so it's going to rotate it this way. And that's going to counteract the net torque due to gravity in this direction, and that's why the thing doesn't rotate out of control. Because again, the torque due to gravity is greater about this point than it was for this point, but the reason you don't have a rotation is because the normal force torque is balancing that. When you add up all the torques, torque due to gravity, front wheel, torque due to gravity, back wheel, torque due to the normal force about the front wheel, plus torque due to the normal force about the back wheel, they obviously sum to zero, because when the men initially stepped on the board, the thing didn't rotate. Okay, so the more interesting question to me, and the reason I decided to make a video for this, is why did the golf cart rotate upon being braked by the driver? So if you want to pause the video to discuss this, feel free to do so. Come back in a minute and we'll talk about it. So why did the golf cart rotate upon being braked by the driver? Okay, I'm going to let you watch a couple of really short videos, and that'll provide you the hint, if you don't already know the answer to that question.
Final time down now. I'm going to just go to the front brake. I'm going to overdo it. Here I go, up, and that rear end comes off the ground. How much braking pressure is available back there now? Zero. I abused it with the rear wheel.
So in both cases, the car popping a wheelie and the bike rotating about the front wheel were caused by counter torques. In the car case, the engine, which is attached to the car, exerted torque on the crankshaft, and the crankshaft exerted an equal and opposite torque on the car, causing it to pop the wheelie. The bike, the brakes, which are attached to the rest of the bike, exerted a torque about the front wheel, and the front wheel exerted an equal and opposite torque on the bike, which resulted in that rotation. So the same thing is happening with the golf cart. Once the brake was applied, this caused a torque in the clockwise direction about the crankshaft to slow the rotation in the counterclockwise direction. The crankshaft exerted an equal and opposite torque in the opposite direction, counterclockwise direction, which is why you saw counterclockwise rotation in the golf cart about that point. So why don't all golf carts rotate counterclockwise about the back wheels when the brakes are applied when moving in the backward direction? If all carts did this, then they probably wouldn't sell a lot of them. The answer is because typically the center of mass is lower and further away from the back wheels. What I've done here is I've simplified the golf cart. The white part is the mass. Here's the approximate location of the rotation point. And here's its center of mass. Okay, when the men boarded it, the center of mass shifted to the left and it also came up. But also mass was added as well. This created a more risky situation than your standard golf cart when there are not people standing on the back of it. Okay, I'm going to compute the moment of inertia for a hypothetical golf cart before the men moved onto the golf cart in this location. A golf cart without people on it, mass is about 454 kilograms. And its dimensions are about 6 feet high and 8 feet long. Now a lot of it's empty. So I'm assuming 3 feet high and 8 feet long in this scenario here. And I'm assuming the mass is equally distributed throughout the area here. So the moment of inertia of a rectangular prism, which is what my approximation is for this golf cart, is this. Mass about this axis. Okay, so an axis right here through the wheel. So it's this length squared plus this length squared times the mass divided by 12 plus mh squared. Okay, this equation gives me the moment of inertia about an axis through the center of mass, but I want to know what the moment of inertia is about this rotation point. So I add m times this distance squared. And again, that's the parallel axis there. And I get 1017 kilograms meters squared. What about for this one? This is an arbitrary shifting of mass. And it's exaggerated a little bit. And I put the center of mass right above the point of rotation. And that's consistent with what we saw. If it were to the left, thing would be rotating before it was braked. I'm going to compute the moment of inertia for this configuration, and this is what I got. 1.74 squared plus 2 squared divided by 12 plus mh squared. So 1008 kilograms meters squared. So it dropped a little bit. So even though the mass increased from 454 to 636, this is just an empty cart. This is with the added mass. So even with the mass increasing, the moment of inertia dropped a little bit, and that's because the mass is much closer to the point of rotation, and because you're squaring the distance from each piece of mass to the point of rotation, shifting the mass closer to the point of rotation reduces the moment of inertia. So here I compute the net torque for this configuration and this configuration. We have two torques here, one due to braking and one due to gravity. For this configuration, torque due to gravity, mg times r sine of the angle between those two vectors, or r perpendicular. And here's my r perpendicular. So that's 454 times 9.8 times 1.2. So 5339 Newton meters. torque due to gravity for this configuration of mass. Negative because it's clockwise rotation, right? Using the right-hand rule, you can see this will provide a clockwise rotation. Plus the torque due to braking is equal to I alpha, right? And the moment of inertia was computed as 1017. Torque due to gravity for this one, 0. Why 0? Because the angle between the gravitational force vector and the r vector is 0. Okay, so sine of 0 is 0. R perpendicular is 0. And that's a bad thing, right? Because gravity's torquing you the right way here. It's torquing you in this direction, towards the ground, right? And you're getting a counter torque from the ground here, the normal force. This is kind of scary because it doesn't take much of a torque to move this thing slightly to the left and induce a rotation due to gravity. Now gravity is going to kick in, because now you have an angle between the force vector and the r vector that's going to cause gravity to push it this way. So as soon as the brakes were applied, you got that counter torque. And I discussed that counter torque is going to be in this direction. For a regular golf cart, you're getting a huge help from gravity. Gravity's torquing you this way. So a counter torque due to braking is not going to make the thing tip over. Here, you're not getting any help from gravity torquing it back, so just a little bit of torque from the braking sent this thing over this way, and then gravity accelerated again once it got the center of mass got beyond the base of support. So, conclude. The smaller, near zero restoring torque due to gravity and the smaller moment of inertia about the back wheel for the scenario where men are on the back will result in a much greater chance of counterclockwise angular acceleration. If the angular acceleration is sufficiently high, then the center of mass could rotate outside the base of support, this scenario, and then gravity will start to torque in the same direction as the counter torque due to braking, and the golf cart will rotate over the back wheel as it did in the video. And again, the torque here, again, back to the right-hand rule, the torque here, where there's my r vector and gravity's down, mg. That's the torque in this direction. That keeps us safe. Get the normal force torque torquing you back. All is good. It's not rotating. Here, the counter torque due to braking sent this point, center mass, to the left. Now the rotation due to gravity looks like this. Here's my r vector pointing from the rotation point to where the force being applied to center mass. Gravity's here. Okay, so right hand rule, right? Here's my r vector, here's mg. Right hand rule through the smaller angle. Now the gravity is going this. Counter torque due to braking, counter torque due to gravity, and now in the same direction. The whole thing rotates over, and a possible extremely dangerous situation.
Shifting the center of gravity the hard way.
Okay, so that concludes my analysis of this episode and this dynamic. I hope that was helpful to you. I hope you see the value of how applying physics can really help you be safe in some cases. Before I knew anything about physics, I would have done probably exactly what those two gentlemen did and step on the back thinking, okay, it's not tilting, I'm good. But I wouldn't have known that that braking provides that counter torque, which rotated the whole thing and sent the center of mass slightly to the base of support, and then gravity kicked in and continued that rotation in the direction which caused it to flip over. So understanding physics can actually prevent catastrophes in many cases. So join me again. I'm going to be doing more of the physics of not so smart stunts, and thanks for watching. Bye-bye.